Hello everyone, welcome back to another video. In this video, we're going to be taking a look at a question from paper 2 HL from the November 2017 batch. And this question involves us looking at the concepts of how to tackle a rate question, how to determine the order of reaction, and how to state a rate expression, and how to calculate the value of the rate constant. And if you don't know what I mean or what any of this means, I'm just going to show that to you in a second. So basically, the order of reaction. What is the order of reaction? This is how I like to think of it. The order of reaction is nothing but us determining how changing the concentration of something in a reaction affects the rate of the reaction. So basically, let's take a look at this equation over here, right? We have this equation, how nitric oxide reacts with chlorine, and they have given us this experimental data here. So some person, okay, we'll just call this person Bob. All right, so Bob conducts 3 trials of experiments. Okay, so he conducts trial 1, 2, and 3. So these are all the same experiments. He's doing the same thing, but all he's done is that he has changed the concentration of certain substances or the certain element, certain substances in each trial. So you have basically two molecules or two substances which are involved in the reaction. You have NO and then you have chlorine gas. So these both are in the gaseous form. And this is the concentration of the gases or of the substances. Now, in the first version or the first time he did the experiment, he had the concentration of NO as 1.3 times 10 to the negative 1 mole dm. So that's the units. And he had chlorine gas at the exact same concentration. And then the rate that he calculated was this. So this rate basically measures how much of the final product, in which case it is NOCl, how much product was produced per minute. So that's the rate. We're not measuring how much was produced, but we're measuring how fast it was produced or how much was produced in a minute. Right? We're measuring the speed, the rate, right? The rate of production. We're not exactly measuring the quantity of production, if that makes sense, right? We are technically measuring the quantity, but we're measuring how much quantity is produced per minute, right? We're trying to see that. We're trying to see the concentration or the amount produced per minute. That's the final goal over here. We're not purely concerned with how much, but how much is being produced per minute. So basically trying to calculate how much is produced at what speed, right? So he from the first version of the experiment, using these two concentrations of our reactants, he has found out that the rate is this much, 3.95 times 10 to the negative 1. Then in the next version of the experiment, Bob, he keeps the concentration of nitric oxide or NO the same, but he doubles the concentration of chlorine, right? He doubles the concentration of chlorine gas. And then what is the effect on the rate? How does this affect the rate? Well, we see that the rate has also doubled, right? The rate has also doubled because 3.95 to 7.9, that's a double, that's times 2. And of course, you can feel free to calculate this on your calculator. This is paper 2, so you can use a calculator. If you want to find out how much the rate has changed or how the rate has changed, all you have to do is you have to divide this number or the second number by the first number. So 7.90 times 10 to the negative 1 divided by 3.95 times 10 to the negative 1. If you put this into your calculator, you'll get the answers too. So that's how you can calculate the change. Of course, I'm sure all of you know how to calculate how much it has changed, right? So I don't have to go into much detail about that. And you can use the same logic to also calculate how much how much Bob has increased the concentration by. It's the exact same thing. Over here, it's quite simple to see because 1.3 times 2 is equal to 2.60. So we know that. Anyways, now in the third version of the experiment, or the third trial, you could say, Bob has kept the concentration of chlorine gas the exact same, right, as the previous experiment. It's the same. He hasn't changed it. But what he has changed is the concentration of nitric oxide, right? And that also has an impact on the initial rate. It has increased. So by how much it has increased? Well, we can just find out by dividing 3.16 by 7.9 times 10 to the negative 1. Put this into your calculator and you'll see that the answer is 4. So this basically tells us that even though Bob only doubled the concentration, right? He's only doubled the concentration of nitric acid, the rate has increase by 4. So we can determine what the effect of nitric oxide or the increase of nitric or decrease of nitric oxide has on the rate, because we're keeping one value stable or constant, and then we are seeing the effect on the other value. And it's the exact same thing for chlorine gas as well. We keep one value the same or one concentration the same, and then we manipulate the other to see how it affects the initial rate. And that's how we're experimentally able to determine what the order of reaction is, or in simple terms, how does the concentration of, or how does changing the concentrations affect the initial rate, or changing the concentration of certain reactants affect the initial rate. That's how we determine it, the order of reaction. Now, if if you double, like we saw in the first in this instance over here, where we double it, we have doubled the concentration of chlorine gas, and the initial rate also doubles. This is called a first order reaction. This basically means that the the quantity or the magnitude by which we change the concentration of one reactant has the exact same effect on the rate. So we double the concentration of chlorine, the rate doubles. If we triple the concentration of chlorine, the rate triples. If we half the concentration of chlorine, the rate will also reduce by half, considering we have kept the concentration of nitric acid constant, right? So that is a first order reaction. It's an identical reaction. You can think of it as a 1-to-1 ratio. So whatever you do to the chlorine gas concentration, the exact same thing will happen to the initial rate concentration, provided that the concentration of nitric oxide that we use is kept constant. Make sense? So the chlorine gas, the order of reaction with respect to chlorine is 1. It's a first order reaction. Now, what about nitric oxide? What is the order of reaction for this? We can see that when we doubled the concentration of nitric oxide while keeping the concentration of chlorine gas the same, we saw that the initial rate quadrupled. So as you can see, there's a 2-to-4 ratio here, or a 1-to-2 ratio. That basically means how much ever you increase or decrease the concentration of nitric oxide by, the initial rate will be impacted double of that, considering that we keep the concentration of chlorine gas the same. So supposing if we increased the concentration of nitric oxide by 6 times, the initial rate will increase by 12 times, because we have doubled. That's the effect on the initial rate. If we halved, or if we halved the concentration of nitric oxide, right, the initial rate would also decrease by 0.25, because that is just the effect. I hope this is making sense to you. What I mean to say is that whatever you do, or however you change nitric oxide, the magnitude by which you change nitric oxide, the initial rate will change double of that, provided that the chlorine gas concentration remains constant. So that's why we call such a reaction a second order reaction, because the ratio, or the effect of the change on, or the effect of the change of concentration of one reactant, that the effect that has on the initial rate is double of what we have actually done to it. And hopefully you can see that over here, that how when we have doubled the concentration of nitric oxide, the rate has quadrupled. So that's why it's called a second order reaction. I know it's a bit confusing, and to be completely honest, even I find it a bit hard to explain it to you in words. This is just something that you have to get with practice and kind of grasp the concept of it. Now, state the rate expression for the reaction. This is very simple. The rate expression is just equal to K, which is a rate constant. We don't know what the rate constant is, so we're going to leave it as K for now, times the concentration of chlorine times the concentration of nitric oxide. But since nitric oxide is a second order reaction, as I mentioned above, we put a little square over here because the rate is affected double of what we do to the concentration of nitric oxide, like I mentioned earlier. So this is the rate expression. I'm just going to take this above. Anyways, I think it'll be easier to write it. So this is basically the rate expression. I'm going to write this above. So it's just K times NO squared times Cl2. This is the rate expression. Now calculate the rate constant at 263 Kelvin. Now how will we do this? How do we do this? Well, it's very easy. The first thing you have to do is take a look at the experimental data, right? Just take a look at the experimental data. Pick one value. Pick one experiment. I'm going to pick experiment 1. Okay. Look at these values. These are the concentrations. This is the initial rate. We're asked to calculate the value of K. Substitute these values, these values, substitute them into our rate expression. So I'm going to say that. So we know that rate in experiment 1, initial rate is 3.95 times 10 to the negative 1. So I can say that 3.95 times 10 to the negative 1 is equal to 1.3 times 10 to the negative 1, because that's the concentration of chlorine in experiment 1, times the concentration of nitric oxide, forgot the K, sorry, times the concentration of nitric oxide, which is also 1.3 times 10 to the negative 1, but this is squared, remember, squared. Now we have these values, and I just want to clarify one more thing. Out of these 3 experiments, you can substitute the values of any experiment. It really does not matter. You can do 1, you can do 2, you can do 3. It doesn't matter, right? Any experiment, the values of any experiment that you choose to substitute will eventually, hopefully, give you the correct answer. I just chose experiment 1 because it's easier for me, and I just think that that would be the best way to go. So let's see what we get as the rate constant. Now, since we have K, which is a variable, it's an unknown on this side, we just have to isolate K, right? This is algebra. This is what we do in math. So it's basically 3.95 times 10 to the negative 1 divided, because remember, if you take this over to the other side, divided by 1.3 times 10 to the negative 1 to the power of 3. Because remember, it's squared over here, and then we multiply it by the same again, so it becomes cubed. Hopefully that makes sense. Now, this is equal to K. Now, if you just plug this into your calculator, which I'm going to do right now, you will also get the right answer. So let's do that real quick. I really hope that my explanations have made sense to you today. So K is equal to approximately 180. So this is the rate constant. And now remember, let's look at this. The rate constant is only applicable to a specific temperature, or to the reaction at a specific temperature. If you change this temperature, the rate constant may change as well. That's just a little bit of a side note. So K is equal to 180. Now, there is also one more part to this. Writing K is equal to 180 is not enough. We have to also write the units. Now, how on earth do you figure out the units? Well, it's also very, very simple. All you have to do is substitute the units into the equation as well. It's the exact same thing. Now you're a bit confused. Wait, what? What do you mean substitute the equation or the units into the equation? How does that make any sense? Well, we know that our equation is rate is equal to K is equal to NO squared times Cl2, right? Now, what is the rate of NO? Sorry, what is the unit of NO? Well, the unit of NO is in mole dm cubed. The unit of Cl2 is also in mole dm cubed, and the initial rate is in mole dm cubed per minute. So just substitute the units into this expression. So it's mole dm cubed per minute is equal to K times mole dm cubed squared, because remember for NO, times mole dm cubed for chlorine. And if you want to find out the units of K, same thing, just isolate K. So that we carry over all of this to this side. And basically, it's mole dm cubed to the minute divided by mole dm cubed to the power of 3, because again, it's the same logic as before. And since we already have 1 mole dm here, we can cancel out this, which leaves us with minute to the power of -1 divided by mole dm squared, because we cancelled out 1 mole dm, so this number reduces by 1. And all you have to do now is to open these brackets, and this basically gives us, I'm going to make some more space here by taking this over here and taking this over here. Now this, when you expand this, or when you square it, you get mole squared dm -6 divided by minute, and then just take this to the numerator. And remember, when you take something from the denominator into the numerator, the signs flip of the exponents, the signs flip. So this basically becomes mole to the power of -2 times dm to the power of 6 per minute. These are the units. This is basically what the units are. I really hope that wasn't too confusing. I hope that you've seen, or that you understand what I've done over here. And that is it for this video. Hopefully you have understood the concept and it hasn't been too much of a challenge for you. If you have not understood what I have done over here, if you're a bit confused, please feel free to reach out to me on my social media. I'll be more than happy to help you out one-on-one. Put down a comment below or send me an email. And as usual, I will be happy to help. So thanks so much for watching. Everyone, have a good day. Goodbye.